March 19th, 1943. Deep inside the Watervliet Arsenal in upstate New York, the air tasted of metal and oil. The night shift had just begun, and in the massive boring mill bay, a single light burned above machine number 7. The concrete floor trembled as the mill's spindle turned, carving the interior of a 16-inch naval gun barrel with a precision that bordered on impossible. Each revolution removed metal in ribbons so thin they glowed orange before curling into the collection pan below. Joseph Whitworth stood beside the machine, his hands black with cutting fluid, watching the dial indicator with an intensity that made younger machinists uncomfortable. He was 51 years old, with silver hair and the kind of silence that came from 30 years of listening to metal speak. The barrel before him stretched 45 feet long, weighed 67 tons, and represented 6 months of forging, heat-treating, and preliminary machining. One mistake now, one deviation of more than 3/1000ths of an inch, and the entire barrel would be scrap. Worse, the battleship waiting for it would go to war with one less weapon. The stakes were written in blood across the Pacific. At Guadalcanal, American battleships had traded salvos with Japanese warships at ranges exceeding 20 miles. The difference between victory and defeat came down to accuracy. A shell that missed by 50 yards was a wasted ton of steel and explosive. A shell that struck home could sink a cruiser, silence a shore battery, or change the course of a battle. But accuracy at 23 miles demanded perfection in the barrel's bore, a straightness and consistency that no one had reliably achieved before the war. Whitworth knew the problem intimately. He had been boring naval gun barrels since 1928, long before the Navy understood what the next war would demand. Back then, the tolerances were looser, the ranges shorter, the consequences less severe. A battleship firing at 8 miles could compensate for slight irregularities in the bore, but the new Iowa-class battleships, with their monster 16-inch, 50-caliber guns, were designed to engage targets beyond the horizon. At those distances, even microscopic variations in the barrel's interior became fatal errors. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Navy's specifications were brutal. The bore had to maintain a diameter of 16.000 inches, plus or minus 0.003 inches, across the entire 45-foot length. The rifling, 60 grooves spiraling through the barrel at a precise rate of twist, had to be cut with equal perfection. Any deviation, any wobble in the boring bar, any flex in the machine, would create what the ballisticians called dispersion, the spreading of shells across the target area instead of concentrating them on a single point. Before Whitworth's innovation, that kind of precision existed only in theory. The massive boring mills used to carve out naval gun barrels were marvels of industrial engineering, but they suffered from a fundamental flaw. The cutting tool, mounted on a boring bar that extended deep into the barrel, would deflect under the enormous cutting forces. Steel is hard, and removing it generates pressures measured in thousands of pounds. The longer the boring bar, the more it flexed. The more it flexed, the less accurate the bore. Engineers had tried everything: heavier boring bars to resist deflection, slower cutting speeds to reduce forces, multiple passes with progressively finer cuts. Nothing worked consistently. Some barrels came out perfect, others showed variations of 5, 10, even 15/1000ths of an inch. The Navy accepted them because they had no choice, but gunnery officers knew the truth. American naval guns were less accurate than they should be, and men were dying because of it. Whitworth had watched this failure for years, studying the problem with the kind of obsession that kept him awake at night. He understood that the boring bar itself was the enemy. No matter how rigid, no matter how carefully supported, it would always flex under load. The solution wasn't to make it stronger. The solution was to change how it cut. In late 1942, he began sketching designs in a notebook he kept locked in his toolbox. The idea was simple but heretical. Instead of a single cutting tool mounted rigidly to the boring bar, he proposed a tool that could float, adjusting its position dynamically as it encountered variations in the metal. It would be spring-loaded, self-centering, constantly seeking the true axis of the bore regardless of how the boring bar flexed. His superiors called it madness. A floating tool, they argued, would chatter and vibrate, destroying the surface finish and ruining the barrel. The whole point of precision machining was rigid control, not allowing the tool to wander. Whitworth listened to their objections, nodded politely, and kept working. At home, in a garage workshop he had built with his own hands, he fabricated the first prototype using springs salvaged from an old Ford truck and tool steel he had purchased with his own money. The design was elegant in its simplicity. The cutting bit sat in a sleeve that could move radially, pushed outward by a precisely calibrated spring. As the boring bar rotated, the spring pressure kept the cutting edge in constant contact with the barrel wall, following its natural centerline rather than the deflected path of the boring bar. The tool would automatically compensate for any flex, any vibration, any irregularity in the setup. In January 1943, Whitworth brought his prototype to the Arsenal superintendent, a man named Colonel Harold Breslin. Breslin was Army Ordnance, a West Point graduate who believed in procedure, regulations, and approved methods. He stared at Whitworth's device with the kind of skepticism reserved for perpetual motion machines. "This is your solution," he said flatly. "A spring and a loose cutting bit." Whitworth met his eyes. "It works, sir. I can prove it." Breslin allowed him one test, one barrel that was already scheduled for rejection due to previous machining errors. If Whitworth's tool made things worse, the experiment would end immediately. If it somehow succeeded, they would consider further trials. The stakes were clear. Failure meant humiliation and the end of 15 months of secret work. Success meant changing how the United States Navy fought its war. On March 14, 1943, Whitworth installed his floating boring tool in machine number 7. The barrel waiting in the mill was a reject, its bore already showing variations of 12/1000ths of an inch from previous attempts. It was destined for the scrap heap, and everyone knew it. The machinists gathered to watch, some curious, most expecting disaster. Whitworth said nothing. He simply started the machine. The sound was different immediately. Instead of the harsh, grinding scream of metal against metal, the tool produced a steady, almost musical hum. The cutting edge found its rhythm, floating on its spring mounting, tracing a path through the steel that followed the barrel's true centerline. Ribbons of metal curled away in perfect spirals, dropping into the coolant bath below. The dial indicator, mounted to measure bore variation, barely moved. After the first pass, Whitworth stopped the machine and measured the bore with a precision gauge. The room fell silent as he recorded the numbers. The variation had dropped from 12/1000ths to 4/1000ths. The machinists looked at each other, unsure whether to believe what they were seeing. Breslin stepped forward, his face unreadable. "Run it again," he ordered. Whitworth made a second pass, then a third. Each time, the variation decreased. By the fourth pass, the bore measured within 2/1000ths of an inch across its entire length, well within Navy specifications. The barrel that had been written off as scrap was now perfect. Breslin stood beside the machine for a long moment, his hand resting on the still warm steel. He turned to Whitworth. "How many of these tools can you make?" Whitworth allowed himself the smallest smile. "As many as you need, sir." By the end of March, every boring mill in the Watervliet Arsenal was being retrofitted with Whitworth's floating tool. The results were immediate and undeniable. Barrels that had taken 8 weeks to machine and still showed marginal accuracy, now finished in 5 weeks with tolerances tighter than anything previously achieved. The rejection rate dropped from 18% to less than 2%. Production accelerated, but the real test would come thousands of miles away, in the Pacific, where battleships built around these barrels would face the Imperial Japanese Navy in battles that would determine the fate of nations. The machinists at Watervliet couldn't know that yet. They only knew that the impossible had become routine, and that a 51-year-old toolmaker had rewritten the rules of precision in a way that no engineer had predicted. Whitworth returned to machine number 7 night after night, boring barrel after barrel, watching his tool work with the satisfaction of a man who had solved a problem everyone else had declared unsolvable. He kept no records of his invention, filed no patents, sought no recognition. To him, the proof was in the metal, in the perfect cylindrical void his tool carved through 67 tons of steel. Each barrel represented a promise, the promise that when the shells flew, they would fly true. In the vast industrial machinery of America's war effort, most innovations arrived through official channels, born in laboratories and approved by committees. Whitworth's floating boring tool was different. It came from the hands of a man who understood that sometimes the solution to an impossible problem isn't more force or better materials, but a willingness to let go of rigid control and trust the metal to find its own truth. The Navy would soon learn what that truth could accomplish. But first, the barrels had to reach the ships, and the ships had to reach the war. In the spring of 1943, that journey was just beginning, and the ocean between New York and the Solomon Islands was still full of submarines, storms, and uncertainty. The barrels travelled in crates, carefully wrapped and labelled, each one carrying inside it the invisible signature of a machinist's forbidden tool, a tool that had learned to float where others had tried to force, and in that floating had found perfection. The story of how one man's insight changed naval warfare wasn't written in official histories or celebrated in newspapers. It was written in the bore of every 16-inch gun that fired from an Iowa-class battleship, etched in microscopic precision across 45 feet of steel. And it began not with genius, but with stubbornness, the refusal to accept that accuracy at 23 miles was impossible just because everyone said it was. To understand why Whitworth's tool mattered, you had to understand what happened when a 16-inch shell left the barrel at 2,600 feet per second. The projectile, weighing 2,700 pounds, spun at 4,000 revolutions per minute as it climbed into the stratosphere, reaching altitudes above 60,000 feet before arcing down toward its target. At 23 miles, the shell spent nearly a minute in flight, buffeted by wind, affected by air density, pulled by gravity into a trajectory that demanded perfect initial conditions. If the barrel's bore varied by even 5,000ths of an inch, the shell would exit at a slightly wrong angle. Over 23 miles, that error amplified into hundreds of yards of dispersion. A salvo that should have concentrated 9 shells into a 200-yard circle would instead scatter them across half a mile. The difference between overwhelming a target and merely annoying it, the difference between sinking an enemy battleship and allowing it to escape. Naval fire control had evolved into a science approaching magic. Analog computers aboard the battleships calculated firing solutions based on target speed, course, range, wind, and the Coriolis effect from Earth's rotation. Fire control officers could predict where an enemy ship would be 60 seconds in the future and aim accordingly. But all of that sophisticated mathematics meant nothing if the barrel couldn't deliver the shell with precision. The weakest link in the chain wasn't the computers or the gunners, it was the bore. Whitworth understood this not from textbooks, but from observation. He had seen the rejected barrels, studied their imperfections, traced the spiral marks left by boring tools that had chattered and deflected. He had watched the Navy accept barrels that met minimum specifications, but fell short of what physics demanded. And he had recognized that the problem wasn't the machinist's skill or the machine's capability. It was the fundamental approach to cutting metal. Every precision machining operation before Whitworth's innovation had relied on rigid tooling. The cutter was locked in place, unable to move, forced to follow whatever path the machine dictated. This worked beautifully for small parts where the cutting forces were manageable and the tools were short and stiff. But for a gun barrel 45 feet long, where the boring bar extended deep into the tube and the cutting forces reached thousands of pounds, rigidity became a liability. The boring bar, despite being 8 inches in diameter and made from the finest alloy steel, would flex. Not much, perhaps only a few thousandths of an inch, but enough to throw off the cut. The deflection varied depending on how deep the tool was in the barrel, how much metal it was removing, even the temperature of the steel being cut. Machinists tried to compensate by taking lighter cuts, but that meant more passes, more time, and still no guarantee of accuracy. Whitworth's insight was to abandon rigidity entirely. Let the tool move, he reasoned, but control how it moves. The spring-loaded mounting allowed the cutting edge to follow the natural center line of the bore, self-correcting for any deflection in the boring bar. It was a form of mechanical feedback, primitive compared to modern servo systems, but revolutionary for 1943. The spring rate was critical, too stiff, and the tool would behave like a rigid cutter, transmitting all the deflection into the bore. Too soft, and it would chatter, bouncing against the metal and destroying the surface finish. Whitworth spent weeks testing different springs, measuring their characteristics, calculating the ideal balance between compliance and control. He filled notebooks with force diagrams and deflection curves, working through the mathematics with a precision that would have impressed university professors. What he created was a tool that thought for itself in a mechanical sense. As the boring bar flexed, the spring pressure maintained constant contact between the cutter and the barrel wall. The tool floated radially, always seeking the true center, always cutting perpendicular to the bore's natural axis. The result was a bore that was straight, not because the machine was perfect, but because the tool adapted to imperfection. The machinists at Watervliet initially distrusted the device. They had been trained to believe that precision came from rigidity, from locking everything down tight and controlling every variable. Whitworth's floating tool violated that principle. It introduced what appeared to be sloppiness into a process that demanded exactness. But the measurements didn't lie. Barrels cut with the floating tool were consistently more accurate than those cut conventionally. Word spread quickly through the ordnance community. By April 1943, engineers from the Naval gun factory in Washington and the Bethlehem steel plant in Pennsylvania were visiting Watervliet to see the tool in action. Some arrived skeptical, carrying their own precision gauges to verify the claims. They left convinced. One Navy captain wrote in his report, "The Whitworth tool represents the most significant advance in gun barrel manufacturing since the introduction of rifling." The Navy ordered immediate adoption across all gun barrel production facilities. Within months, boring mills in Washington, Pennsylvania, and Maryland were equipped with floating tools based on Whitworth's design. Production rates increased while quality improved, a combination that rarely occurred in manufacturing. The bottleneck that had limited battleship construction was suddenly opened, but Whitworth himself remained largely unknown. The Navy classified his invention under wartime secrecy regulations, forbidding publication or public discussion. No patents were filed. No press releases announced the breakthrough. The floating boring tool became one of thousands of invisible innovations that won the war without fanfare. Whitworth received a small bonus payment, a commendation letter from the Secretary of the Navy, and orders to continue producing barrels at maximum rate. He accepted this obscurity without complaint. Recognition had never been his motivation. The work itself was reward enough, the satisfaction of solving an impossible problem and seeing the solution replicated across the country. Every night, returning home to his modest house on 3rd Street in Watervliet, he would stop at the garage and examine the original prototype still hanging on the wall. It looked crude compared to the refined versions now in production, but it had proven the concept. His wife, Margaret, understood his obsession without sharing it. She had watched him work through countless nights, sketching designs at the kitchen table, muttering about spring rates and cutting forces. When he finally succeeded, she noticed the change immediately. The tension left his shoulders. His sleep became peaceful. He had been carrying the weight of those gun barrels for years, and now he had set it down. The first Iowa-class battleship to receive barrels made with Whitworth's tool was USS New Jersey, commissioned in May 1943. Her 9 16-inch guns, arranged in 3 triple turrets, represented the pinnacle of American naval artillery. Each barrel had been bored to tolerances that previous generations of machinists would have considered impossible. The guns were test-fired at the Dahlgren Naval Proving Ground in Virginia, where ballisticians measured their accuracy with instruments sensitive to fractions of a degree. The results exceeded every prediction. At 23 miles, the guns placed shells within a circle measuring just 180 yards in diameter, nearly half the dispersion of earlier battleships. Fire control officers recalculated their probability of hit tables and discovered they could engage targets at ranges previously considered speculative. The Iowa class wasn't just more accurate than older battleships, it was operating in a different category of precision entirely. In August 1943, USS New Jersey steamed out of the Philadelphia Navy Yard bound for the Pacific. Her gun barrels, still gleaming with protective cosmoline, carried within them the invisible legacy of a machinist's forbidden tool. The crew of 2,700 sailors had no idea that the accuracy of their main battery had been revolutionized by a 51-year-old man working night shifts in upstate New York. They only knew that their guns could reach farther and hit harder than anything the Japanese Navy possessed. The ship's gunnery officer, Commander William Thompson, had reviewed the test-fire data with a mixture of excitement and disbelief. His previous assignment had been aboard USS Washington, an older battleship whose 16-inch guns were excellent by pre-war standards, but plagued by dispersion problems. He knew intimately the frustration of watching salvos straddle a target without scoring hits. Now, studying New Jersey's capabilities, he realized he was commanding a weapons system that rewrote naval warfare's fundamental equations. Thompson gathered his fire control team during the Pacific crossing and explained what they possessed. "Gentlemen," he said, "we can hit targets our predecessors couldn't even see. Our responsibility is to make every shell count. The Japanese will learn to fear our accuracy more than our volume of fire." He wasn't exaggerating. In the coming months, New Jersey would demonstrate a level of precision that became legendary among both American and Japanese naval officers. But before those battles could be fought, the ship had to reach the war zone. The crossing took 3 weeks, steaming southwest through the Panama Canal and across the vast Pacific. The gun crews drilled constantly, loading the massive shells, training the turrets, practicing the intricate choreography of naval gunnery. Each shell weighed as much as a small car. Each required a team of 20 men to load, ram, and fire. The coordination had to be perfect. The timing synchronized across all 9 guns. Below decks, in the ship's machine spaces, other crews maintained the engines, generators, and pumps that kept New Jersey alive. The battleship was a city unto itself, carrying fuel, ammunition, food, and water for extended operations, far from any port. Every system had to function flawlessly, because failure at sea, especially in combat, meant death. The men understood this. They had volunteered for a ship whose primary purpose was to sail into harm's way and strike the enemy with overwhelming force. As New Jersey approached the Solomon Islands in September 1943, intelligence reports painted a grim picture. Japanese naval forces, though battered by months of fighting, remained formidable. Their battleships, particularly the Congo-class fast battleships, were aggressive and well commanded. American victories at Midway and Guadalcanal had shifted the strategic balance, but individual battles remained fiercely contested. The arrival of Iowa-class battleships would tip that balance further, but only if their superior capabilities translated into combat effectiveness. The first test came on November 10, 1943, during the bombardment of Tarawa. New Jersey, along with several other battleships, was assigned to soften Japanese defenses before the marine amphibious assault. The targets were coastal fortifications, bunkers built from reinforced concrete and coral, designed to withstand anything short of a direct hit. Previous bombardments had proven frustratingly ineffective. Shells landing nearby did little damage. Only precise hits could destroy the bunkers. Commander Thompson studied the fire control solution as New Jersey approached the bombardment position. The range was 19 miles, well within the gun's capabilities but challenging due to the small size of the targets. Each bunker presented a footprint of perhaps 30 yards by 20 yards. At that distance, hitting such a target required both accuracy and luck. Thompson ordered the main battery to commence firing, and the forward turrets erupted in flame. The sound of a 16-inch gun firing is beyond description. It's not merely loud. It's a physical force that compresses the air, rattles bones, and momentarily stops the heart. Observers standing on deck, even wearing ear protection, felt the shockwave as a blow to the chest. The muzzle blast blew smoke and flame 200 feet outward. The ship itself recoiled, her 60,000-ton hull shifting sideways in the water from the recoil force. The shells climbed into the morning sky, arcing over the horizon, disappearing into the clouds. For nearly a minute, there was nothing but waiting. Then, on the distant shore, columns of sand and coral erupted skyward. Spotting aircraft radioed corrections. The first salvo had landed 200 yards over. Thompson adjusted the fire control solution and ordered a second salvo. This time, the shells landed within 50 yards of the target bunker. The third salvo scored a direct hit. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The concrete structure disintegrated, blown apart by the impact of a 2,700-pound projectile travelling at 1,800 feet per second. The explosive force was equivalent to a small bomb, but it was the kinetic energy, the raw momentum of 1.5 tons of steel hitting solid matter, that did the real damage. The bunker simply ceased to exist, vaporized into fragments no larger than a fist. Thompson watched through binoculars as the smoke cleared. He turned to his fire control team with quiet satisfaction. That, gentlemen, is what precision looks like. Mark the next target. Over the next 4 hours, New Jersey systematically destroyed 18 fortified positions, using an average of 4 shells per target. Previous bombardments had expended hundreds of shells to achieve similar results. The improvement wasn't marginal, it was revolutionary. The Marines who landed at Tarawa later that day found sections of the beach where Japanese defences had been completely obliterated. Bunkers that should have required flamethrowers and satchel charges to clear were already rubble. One Marine captain, surveying the destruction, radioed back to the fleet. "Whoever's shooting those 16-inch guns, tell them they just saved a lot of lives." The message reached New Jersey's bridge. Commander Thompson read it aloud to his crew. They cheered, understanding that their weapon system had passed its first test. But Tarawa was only the beginning. In the months that followed, New Jersey and her sister ships would face increasingly difficult challenges. Shore bombardment was one thing, ship-to-ship combat was another entirely. The Japanese Navy, despite its losses, still possessed battleships armed with 14-inch and 16-inch guns of their own. When those ships clashed, accuracy would determine survival. The side that scored first hits would likely win the battle. The opportunity came in November 1944, during the Battle of Leyte Gulf, the largest naval engagement in history. Japanese forces, attempting to disrupt American landings in the Philippines, sent their remaining battleships into a desperate attack. Among them was Yamato, the largest battleship ever built, armed with 9 18-inch guns that outranged and outweighed anything the Americans possessed. On paper, Yamato was invincible. In practice, she had never faced an Iowa-class battleship with guns bored by Whitworth's tool. USS Iowa and USS New Jersey, operating as a fast battleship division, intercepted the Japanese force on the morning of October 25th. The range opened at 32,000 yards, over 18 miles. Fire control radars locked onto the enemy ships, feeding data to analog computers that calculated firing solutions with mechanical precision. The Iowa-class battleships fired first, their guns elevated to maximum angle, launching shells on trajectories that would take them into the stratosphere before descending onto their targets. The Japanese ships returned fire moments later. The ocean between the two fleets became a battlefield of falling steel, columns of water erupting where shells missed, flashes of light where they hit. At these extreme ranges, the human eye couldn't track individual shells. The battle was fought by mathematics and machinery. Men feeding data into computers, computers directing guns, guns hurling shells across distances that defied comprehension. Iowa's first salvo straddled the lead Japanese battleship, 3 shells falling short, 3 beyond. The fire control team adjusted and fired again. This time, 2 shells struck home, one penetrating the forward turret, the other hitting the superstructure. The Japanese ship staggered, smoke pouring from the damage. New Jersey engaged a second target. Her guns trained on a Congo-class fast battleship attempting to close range. Commander Thompson watched the fall of shot through his optical rangefinder, calling corrections to his fire control officer. The precision that Whitworth's boring tool had built into those barrels now expressed itself in combat. Where older battleships would have required 10 or 15 salvos to score hits at extreme range, the Iowa-class ships were hitting with their 3rd or 4th. The advantage was decisive. Japanese gunnery officers, trained to expect American shells to scatter widely, found themselves targeted with accuracy they hadn't anticipated. Their own shells, fired from barrels made to looser tolerances, couldn't match the consistency of the American guns. Over the next hour, the battle turned into a demonstration of how precision manufacturing translated into combat superiority. The Japanese battleships, though courageously fought, were systematically battered by American shell fire. Hits from 16-inch armor-piercing shells penetrated deck armor, detonated magazines, started fires that consumed entire sections of the ships. The American battleships, benefiting from superior fire control and tighter bore tolerances, remained relatively undamaged. By noon, 3 Japanese battleships were sinking or burning, their crews abandoning ship. The surviving vessels retreated, pursued by American cruisers and destroyers. The Battle off Samar, as it came to be known, represented the last time battleships fought battleships in the Pacific. The Japanese Navy would never, again, risk its capital ships in a gun duel. The era of the battleship as the dominant naval weapon was ending, but for one brief moment, American naval artillery had reached the peak of its development. Aboard New Jersey, Commander Thompson surveyed the damage to his ship. A few shell splinters had scarred the superstructure. One secondary gun mount was out of action, but the main battery, those 9 16-inch rifles bored to impossible precision, remained intact and ready. He ordered the guns to cease fire and secured from battle stations. The crew, exhausted and deafened, moved through their post-battle routines with practiced efficiency. In the coming days, when naval analysts reviewed the battle, one statistic stood out. The Iowa-class battleships had scored hits with 28% of their main battery shells at ranges exceeding 18 miles. Previous American battleships averaged 7%. The Japanese, firing from ships whose gun barrels suffered from greater manufacturing variations, hit with less than 4% of their shells. The difference wasn't crew skill or tactical doctrine. It was the precision built into every inch of those gun barrels. Back at Watervliet Arsenal, Joseph Whitworth read about the battle in the newspapers, though the accounts were heavily censored and gave no details about gunnery performance. He knew, though, the Navy had sent him a classified letter of commendation, noting that his technical innovation had contributed significantly to combat success in the Pacific theater. The letter was polite and bureaucratic, but Whitworth understood what it meant. The barrels he had bored were keeping men alive and sinking enemy ships. That was all the recognition he needed. He returned to machine number 7 and continued his work. There were more barrels to bore, more battleships to arm, more battles to fight. The war would not end for another 9 months, and during that time, Whitworth would personally supervise the boring of 83 16-inch gun barrels. Each one passed inspection with tolerances well within specifications. Each one carried his invisible signature, the mark of a tool that had learned to float where others had tried to force. The machinists who worked alongside him noticed a change in how he approached the work. Before his breakthrough, he had been tense, frustrated by the limitations of conventional boring methods. After, he was calm, almost serene. He had solved the unsolvable problem, and now he was simply executing the solution over and over, each barrel a repetition of the first successful cut. There was a zen-like quality to his focus, a complete absorption in the perfection of the process. One evening, a young machinist named Robert Chen asked him how he had thought of the floating tool. Whitworth paused, considering the question. "I stopped trying to control the metal," he said finally, and started listening to what it wanted to do. The boring bar was always going to flex. The barrel was never going to be perfectly set up. Those were facts I couldn't change. So I built a tool that worked with those facts instead of against them. Chen nodded, though he wasn't sure he fully understood. It would take years of experience before he could appreciate the wisdom in those words. Precision machining, Whitworth continued, isn't about forcing metal to obey you. It's about understanding how metal behaves and creating conditions where it naturally does what you need. The tool doesn't fight the deflection, it adapts to it. That's the secret. He turned back to the machine and started another cut. The familiar hum filled the bay, the sound of metal yielding to patience and insight. Chen watched for a while longer, then returned to his own machine, carrying with him a lesson that had nothing to do with springs or cutting angles. Sometimes the solution to an impossible problem was to stop demanding the impossible and work with what was actually achievable. By the time the war ended in August 1945, American naval artillery had established a reputation for accuracy that impressed even the British Royal Navy, whose gunnery traditions stretched back centuries. British naval observers who witnessed American battleships in action filed reports noting the exceptional consistency of American main battery fire. Some attributed it to superior fire control systems, others credited better training. A few perceptive analysts noted that American gun barrels seemed to maintain their accuracy longer than British guns, suggesting differences in manufacturing quality. The truth remained classified. The floating boring tool was still considered a military secret, part of the technical advantage that had helped win the war. Whitworth received no public recognition, no newspaper interviews, no place in the history books. The Navy promoted him to master machinist, increased his salary, and assigned him to train the next generation of gun barrel makers. He accepted these honours with the same quiet dignity he had shown throughout the war. In 1948, with the war long over and the secrecy restrictions lifted, Whitworth finally filed a patent for his floating, boring tool. The Patent Office granted it after only cursory examination. By then, the innovation had become standard practice across the ordnance industry. Every major gun barrel manufacturer in America used some variation of Whitworth's design. The tool had evolved, becoming more sophisticated, but the core principle remained unchanged. Let the tool find the true center line instead of forcing it to follow a rigid path. Whitworth retired in 1952 at the age of 60. He had spent 43 years as a machinist, the last 9 refining and applying the innovation that had changed naval warfare. His pension was modest, his savings adequate but not generous. He lived quietly, tending a small garden behind his house, occasionally consulting for the Arsenal on particularly difficult machining problems. He never spoke about the war years, except in technical terms, discussing tolerances and spring rates, but avoiding any mention of the battles his barrels had fought. In 1961, a young naval historian researching the Iowa-class battleships discovered a reference to Whitworth's tool in a declassified Navy technical report. Intrigued, he tracked down Whitworth and requested an interview. Whitworth agreed reluctantly. They met at the Arsenal, where machine number 7 still operated, though it had been modernized with electronic controls and hydraulic systems that would have seemed like science fiction in 1943. The historian asked about the inspiration for the floating tool. Whitworth thought for a long moment before answering. "I watched a lot of barrels fail inspection," he said, "and I asked myself why. The answer was always the same. The boring bar flexed, so I asked a different question. What if instead of trying to prevent the flex, we accommodated it? Once I asked the right question, the solution became obvious." The historian pressed for details about the combat effectiveness of the barrels. Did Whitworth know how many ships his innovation had helped sink, how many American lives it had saved? Whitworth shook his head. "I made barrels," he said quietly. "Other men fired them. I did my job. They did theirs." He refused to claim credit for victories won by sailors thousands of miles away, but the numbers, when the historian later compiled them, told a story Whitworth wouldn't. Between 1943 and 1945, American battleships armed with barrels bored using Whitworth's tool fired approximately 12,000 rounds in combat. Their hit rate at ranges exceeding 15 miles was documented at 24%, nearly triple the hit rate of battleships with conventionally bored barrels. In naval engagements where American and Japanese battleships exchanged fire, the American ships consistently landed the first damaging hits, providing a decisive tactical advantage. The strategic implications were profound. Accurate naval gunfire allowed American forces to neutralize shore defenses with fewer shells, reducing the need for massive ammunition stockpiles and freeing cargo space for other supplies. It meant amphibious assaults faced less resistance, saving marine lives. It meant enemy ships hesitated to engage American battleships, knowing they would be outshot at any range. The cumulative effect of Whitworth's innovation rippled through every naval operation in the Pacific. Yet, for all its impact, the floating boring tool remained obscure. While radar, atomic weapons, and code-breaking captured public imagination, the mundane work of precision manufacturing went unnoticed. No monuments were built to honor machinists. No films depicted the drama of boring mills and dial indicators. The heroes of American industry worked in anonymity, their contributions measured in thousandths of an inch rather than headline victories. Whitworth embodied this anonymous excellence. He never sought fame, never demanded recognition, never complained about obscurity. To him, the work itself was meaningful, the satisfaction of solving an impossible problem, of seeing his solution replicated across the country, of knowing that somewhere in the Pacific his barrels were performing exactly as designed. That was reward enough. He understood that most essential work goes unrecognized, and he was content with that reality. In his final years, Whitworth occasionally visited the Arsenal's museum, where a 16-inch gun barrel stood on display. The placard mentioned the barrel's specifications, its weight, its range, but said nothing about how it had been manufactured or who had made its precision possible. Whitworth would stand beside it for long minutes, running his hand along the cold steel, feeling the rifling grooves beneath his fingers. He knew every inch of that bore, could visualize the cutting tool that had carved it, could hear the sound of the machine that had turned it. One day, a group of schoolchildren touring the museum gathered around the barrel. Their teacher explained that this gun could fire a shell weighing more than a car over 23 miles. One child asked how they made it so accurate. The teacher admitted she didn't know, suggesting it must have been difficult. Whitworth, standing nearby, smiled, but said nothing. The answer would have taken hours to explain, and even then, they wouldn't understand. Precision wasn't a single innovation. It was 1,000 small decisions, a relentless attention to detail, and a willingness to question assumptions everyone else accepted. The floating boring tool represented something larger than its mechanical function. It embodied a philosophy of problem-solving that rejected brute force in favor of elegance. Instead of building bigger, stiffer, boring bars, Whitworth had created a tool that worked with the system's inherent limitations. Instead of fighting deflection, he had accommodated it. This approach, letting the solution emerge from understanding rather than imposing it through force, was applicable far beyond machining. Engineers studying Whitworth's patent in later years recognized its broader significance. The self-correcting mechanism, the use of spring pressure to maintain constant contact, the acceptance that rigid control was sometimes inferior to adaptive response, these principles influenced fields ranging from automotive suspension design to precision optics manufacturing. The tool's descendants appeared in contexts Whitworth never imagined, proof that truly elegant solutions transcend their original applications. By the 1960s, the era of the battleship had ended. Guided missiles and aircraft carriers dominated naval warfare. The massive 16-inch guns fell silent, their ships decommissioned or converted to museums. The Iowa-class, battleships, those floating testaments to American industrial power, became tourist attractions where visitors could peer into turrets and imagine the fury of their broadsides. But the barrels themselves, those 45-foot tubes of precision-bored steel, remained as remarkable as ever. Modern machinists examining those barrels with laser measurement equipment expressed amazement at their tolerances. Even decades after manufacture, even after firing thousands of rounds, the bores remained within specifications that challenged contemporary manufacturing capabilities. The barrels had been built to last centuries, precision frozen into steel through techniques that seemed almost artisanal compared to modern computer-controlled machining. Yet they equaled or exceeded what modern technology could achieve. Whitworth died in 1973 at the age of 81. His obituary in the local newspaper mentioned his 43 years at the Arsenal and his retirement as master machinist. It noted that he had contributed to wartime manufacturing efforts but provided no details. His funeral was attended by family, a few former colleagues, and several machinists who had learned their trade under his supervision. They remembered him as demanding but fair, a perfectionist who believed that good work was its own justification. His widow, Margaret, donated his notebooks to the Arsenal's archives. The librarian who catalogued them found detailed sketches of the floating tool's evolution, calculations of spring rates and cutting forces, observations about metal behavior under stress. The notebooks revealed a mind that thought deeply about fundamental problems, that questioned accepted wisdom, that persisted through failure until success emerged. They also revealed humility. Whitworth never claimed genius. His notes were filled with phrases like, "tried this, didn't work," and "need to think more about why this fails." In 1991, the American Society of Mechanical Engineers designated Whitworth's floating boring tool a historic mechanical engineering landmark. The ceremony took place at Watervliet Arsenal, where machine number 7, long since retired, stood preserved in a corner of the manufacturing complex. Engineers from across the country attended, along with several elderly Navy veterans who had served aboard Iowa-class battleships. They spoke about accuracy, about precision, about the invisible contributions that had won the war. One veteran, a former fire control officer, described watching New Jersey's guns systematically destroy enemy fortifications at ranges that seemed impossible. "I never knew why our guns were so accurate," he said. "We just trusted they were. Now I understand it was because of men like Joseph Whitworth, who cared about their work enough to make it perfect." The audience applauded, though Whitworth wasn't there to hear it. His legacy had finally received public recognition 2 decades after his death. Boring tools principle continues to influence modern manufacturing. Computer-controlled machining centers often incorporate adaptive tooling that adjusts to variations in workpiece hardness or machine deflection. The mathematics are more sophisticated, the sensors more precise, but the underlying philosophy remains Whitworth's. When rigid control is impossible, adaptive response becomes the solution. Let the tool find its path rather than forcing it. Today, if you visit the Battleship New Jersey Museum in Camden, you can tour the 16-inch gun turrets and see where those massive shells were loaded and fired. The tour guides explain the gun's range, their power, their role in Pacific battles. They mention fire control computers and radar systems, but they rarely mention the boring process that created the barrel's precision, or the machinist whose forbidden tool made that precision achievable. History remembers the weapons and the warriors, but forgets the toolmakers. Yet without Whitworth's innovation, those guns would have been less accurate, those ships less effective, those battles harder fought. The floating boring tool represents one of countless invisible contributions that shaped the war's outcome. Not glamorous, not dramatic, but absolutely essential. The difference between hitting a target at 23 miles and missing it by 200 yards was measured in thousandths of an inch, and those thousandths were carved into steel by a tool that knew when to let go. In the end, Whitworth's story is about the power of questioning assumptions. Everyone accepted that large gun barrels would have accuracy limitations due to boring bar deflection. That was simply how things were. Whitworth refused to accept it. He asked why, then asked what if, then built something that shouldn't have worked but did. His willingness to challenge conventional wisdom, to trust his own observations over established practice, to risk failure in pursuit of a better solution, that was his real innovation. The floating tool was merely how that innovation expressed itself in steel. The lessons extend beyond machining, beyond manufacturing, beyond even engineering. Any field dominated by accepted limitations needs its Joseph Whitworths, people willing to question why things can't be done and to imagine how they might. Progress doesn't come from accepting impossible. It comes from refusing to believe in impossible until you've exhausted every alternative. Whitworth spent 15 months working secretly on a solution everyone said wouldn't work. When it did work, he changed naval warfare without firing a single shot. His legacy lives in the precision we now take for granted, in the manufacturing tolerances that enable modern technology, in the understanding that sometimes flexibility achieves what rigidity cannot. Every time an adaptive control system adjusts a cutting tool, every time a self-correcting mechanism compensates for imperfection, Whitworth's insight echoes forward. He taught metal to find its own truth, and in doing so, taught engineers to trust adaptation over force. The 16-inch gun barrels stand silent now, monuments to an era when the measure of power was the weight of shell you could hurl across the horizon. But their precision remains, frozen in steel, testament to a machinist who believed that impossible was just another problem waiting for the right question. Joseph Whitworth asked that question, found the answer, and changed the world 1,000th of an inch at a time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.